Okay, so let's talk about something huge, the global shipping industry. I mean, this is a massive, intricate machine that moves, well, pretty much everything you own across the planet. And at its heart, there's this puzzle. A puzzle so complex, so enormous, that it basically breaks our most powerful computers. Today, we're going to look at a totally new way of thinking that might just crack this thing wide open. And if you want to get a sense of this scale here, just look at this number, 80%. Over 80% of all global trade travels by sea. Now, that's not just some random statistic, right? That's the lifeblood of our entire economy. It's the engine that stocks the shelves in your local store, that delivers the parts to build your car. So you can imagine making this system even a tiny bit more efficient, the ripple effects would be absolutely massive. So yeah, you can think of these shipping lanes as the arteries of world trade. But figuring out the best path, it is so not as simple as just drawing a line on a map. No way. You've got to decide which of the thousands of ships is going to carry which cargo from which port to which destination. And you have to do all of that while juggling fuel costs, ship speeds, delivery times, the weight of the cargo. I mean, it is a total logistical nightmare. And this puzzle, it actually has a name. It's called the Vehicle Routing Problem, or VRP for short. It's like a classic textbook challenge in logistics. Only here, the vehicles are these gigantic cargo ships, and the customers are all the ports around the world waiting for their stuff. And the goal, the whole point, is to find the one single, absolute lowest cost solution for the entire fleet. And let me tell you, it is brutally difficult to solve. And when I say difficult, I'm not kidding. It's in this special class of problems computer scientists call NP-hard. Now, what does that really mean? Well, for a problem like this, every time you add just one more ship or one more port, the number of possible routes just explodes. It grows exponentially. So trying to just brute force it, check every single possible option, it would literally take a supercomputer longer than the age of the universe. So yeah, we need a totally different kind of tool. So, okay, if our regular classical computers just can't handle it, what's the alternative? What kind of tool could possibly tackle this monster of a problem? Well, the answer comes from a completely different way of looking at computation itself. We're talking about quantum computing. All right, first things first, let's get one thing straight. A quantum computer isn't going to replace your laptop or make Netflix load faster. Not at all. Think of it more like a specialized tool, like a Formula One race car. It's built to do one very specific thing, but do it incredibly well. And that one thing is tackling these huge, messy optimization problems. You see, instead of using bits that are either a 0 or a 1, they use something called qubits, which can kind of be a 0 and a 1 at the same time. And this weird property lets them explore a mind-boggling number of potential solutions all at once, which, it turns out, is exactly what you need for a puzzle like this one. So here's the really clever part. The big idea in the research we're diving into today isn't about ditching our classical computers. Not at all. It's about creating a kind of hybrid dream team. You pair a quantum processor with a classical one, and you let each of them do what they're best at. And this is how they split up the work. It's a perfect division of labor. You've got the quantum computer, the route finder, tackling the really gnarly NP-hard part of the puzzle. That's the which ship goes where with what cargo mess. It's exploring this insane number of possibilities. Then, once it has a potential set of routes, it just hands it off to its teammate, the classical computer, the speed calculator. And the classical computer does the straightforward math. What's the best speed for these routes? And what's the final cost? Simple. So how does this dream team actually communicate? Well, it's this really clever feedback loop. They call it alternating optimization. So step 1, the quantum algorithm suggests a set of routes. Step 2, the classical computer crunches the numbers for those routes and spits out a total cost. Step 3, that cost gets fed back to the quantum part, which uses that information to make a better, smarter guess next time. And this loop just keeps going, repeating over and over, with each cycle getting them closer and closer to the perfect answer. Okay, so that's the theory. It sounds pretty elegant, right? But the big question is, does it actually work? I mean, in practice. Well, the researchers put this whole hybrid system to the test. And what you're looking at here is basically the quantum algorithm's thinking. See all those crazy spikes and dips at the beginning for the first 60 or so tries? That's the system just exploring a massive range of different possibilities, trying things out. But then, look what happens. It starts to settle down, to stabilize, it converges. It's zeroing in on a single, stable, low-cost solution. It's literally learning the best answer as it goes. And this is the payoff. This is the big result. The hybrid method they came up with found a total cost of about $576,000.
Now get this, that is the exact same number that the brute force method found. And remember the brute force method? That's the one that would take longer than the age of the universe on a real problem. So this hybrid team found the perfect answer way faster, and it blew the other, simpler methods out of the water. The bottom line? The concept works.
Okay, so this is way more than just a cool experiment for a research paper. This is a proof of concept. It's a signpost pointing towards a future where we could completely transform how we manage, well, everything. So, why should you care about all this? Well, a hyper-efficient logistics network means lower costs for shipping companies, and that can mean more stable prices for, well, everything we buy. But maybe even more important, when you optimize these routes and speeds, you burn less fuel, a lot less fuel. That means a smaller carbon footprint for a massive global industry. And this isn't just about ships. This whole method is like a blueprint. You could apply it to airlines, to trucking fleets, to your local delivery services, basically anywhere you have the same kind of complex routing puzzle. You know, the researchers themselves put it best in their paper's conclusion. They said their work highlights this hybrid quantum classical method as a promising approach for maritime transport and other complex logistics problems. That's a huge stamp of approval for this new way of thinking. And that really leaves us with a pretty mind-blowing final thought. We've just seen how it's possible to solve a puzzle that we used to think was literally impossible to compute. So if these quantum classical teams can unravel the insane complexity of global shipping, you gotta wonder, what's next? What other huge, impossible challenges in medicine or finance, or maybe even climate science, are they about to solve?